Welcome to RFIC class. This is lecture 13 unit 2, and in today's class we'll look at direct conversion receiver architecture and some of the issues related with direct conversion receiver. So far in the previous lectures we have come across different types of architecture, starting from simple heterodyne, dual IF receiver, image reject receivers like Hartley and Beaver architecture. And in the Weaver architecture, we have looked at something called as secondary image, and to resolve secondary image, one solution what we proposed yesterday, the previous classes, to generate second IF as 0. The same principle or the idea behind this direct conversion receiver also remains same. So when we say it is direct conversion, the basic idea is actually to translate the RF spectrum directly to the baseband. So when we call this as direct conversion receiver, otherwise we call this as DCR, direct conversion receiver, otherwise we call it as DCR. Idea is actually to translate RF input or spectrum to the baseband. So generally this is done in steps. In heterodyne receiver, we use something called as intermediate frequency, where your RF input is first converted into an intermediate frequency and later it will be converted into a lower frequency. But that used to happen in different stages. But here in direct conversion receiver, we are directly translating the RF spectrum into baseband. So I should write here, this happens in the first down conversion itself. So you may be wondering then why we should not do this before, or why all this heterodyne and other architectures we were discussing. Yeah, so when we say this is very simple, we can directly translate into baseband, but this receiver this receiver has a lot of other issues also along with it. But when I say there are some issues, there are some advantages also. That is the whole reason why we are studying actually about direct conversion receiver. So since we are translating the RF spectrum into baseband in the first down conversion, we call them as direct conversion receiver, or otherwise we call it as 0 IF receiver, because the intermediate frequency there is no intermediate frequency. It is directly translated into baseband. Or since there are no mixing of two different frequency, we call this as homodyne receiver also. Homodyne receiver also, right? So these receivers are popular, but this receiver come with a lot of issues with it. So before looking at the various issues of this direct conversion receiver, let us look at the benefit side, or why we need to look for direct conversion receiver. So I hope this is clear. What happened in a heterodyne receiver is this. So in a heterodyne receiver, you will have a mixer, and there will be an RF input and there will be an LO input. Typically, LO input will be selected such a way that we can generate a IF output, intermediate frequency. Right. So here we write it as omega IF. There is an intermediate frequency which is omega RF minus omega LO if it is down conversion. Right. So this is what used to happen in a heterodyne. Now, in the case of homodyne receiver, or in the case of direct conversion receiver, we have this. We do have a mixer which is actually receiving an RF input. Now, we should provide an LO. We should provide an LO such a way that your omega LO is equal to omega RF. So that directly what we get here is a signal to baseband. So this is the difference, right? Or your omega IF remains 0 since your omega LO is equal to omega RF. I hope this is clear. So let us look at some of the benefits. Okay, can I get some response from your side? So what do you think are the benefits of this direct conversion receiver? You can put your responses in the chat box. Yeah, Ankur, very good. No image, no image, very good. Yes, that is one of the main. That is one of the highlight of this direct conversion receiver. There are no image problem or absence of image. Now, when you say there are no image, along with that, there are a lot of other advantages coming in, right? All right, Nagaraj. Yeah. So when you provide two signals of same frequency to a mixer, what will be the result of the mixing process? So generally we look for a sum and difference component, right? So since both are at equal frequency, the difference component will be directly going to baseband, right? Zero. Baseband, since it is directly falling as a at zero. Yes, Nagaraj, I hope it is clarified. Yeah, so one important thing is when we say there are no images, there are added benefits along with that. Can you just tell me what are the benefits? Yeah, Anirudh, I just saw your response. So center frequency will be DC. You meant to say that the down converted signal? Yes, it will be to the baseband. It will be to the DC. Yes. Yeah, so that depends on the modulation scheme, right? Especially in, yeah, that depends on the modulation schemes, Nagaraj. So it can be either in amplitude or in phase. Yeah, that is possible. Now, Siddharth is asking how is yeah, yeah. Another point is, yes, very good. Channel selectivity is better because since there are no images, there are no difficulty in designing, there is no need to design a lot of filters with a lot of selectivity, right? So that is not there. So whenever you are coming out of the problem of image, along with that, there are a lot of other benefits too. Yes. Even we can say that the channel selection, in order to select a particular channel, we don't need to design a band pass filter or a band select filter. Since it is pushed to the base band, you can use a low pass filter, and most of the low pass filter, even you can go for active implementation on ICs. Yeah. All right, Siddharth. Okay. Yeah. I hope I answered your question, Siddharth. So there will not be images because the LO frequency is equal to the RF input frequency.
Yes, sir.
Okay. Yeah. So let me just put some of the benefits or advantages of direct conversion receiver. So the main advantage or the advantage what we are looking for is the advantages of no image. So I can write it as absence of image, and this will greatly simplify the design process because we know when we had image in all the discussion, at least for the previous 3 to 4 classes, we were discussing about how we can remove the images, how we can cancel the images, right? So this will greatly simplify the design process, the entire design. By we can when I say it will simplify the design process, especially on the area of filters, right? So that is the very important and highlight of this direct conversion receiver. Followed by this, we can say that we know in heterodyne receivers we do band selection and channel selection, and even in multiple down conversion scenario there we were employing various band pass filters. Now since it is directly to baseband, we can actually employ channel selection with the help of low pass filters itself, right? It can be performed by a low pass filter. And so compared to band select or band pass filters, the realization on chip is comparatively simple when we look for a low pass filter, right? Because even the frequency what we are looking is actually very low. So on-chip implementation is easy for a low-pass filter, but when it comes to band-pass filter, we may need to incorporate inductors or other passive components into it, right? So again, when it is since we know that the signal is now located near to baseband, um, the requirement of very sharp cutoff filter, like whenever we go for band pass filter, we are actually we want to select something in between, right? So we know the response of band pass filter is something like this. So we greatly depends on the selectivity or the sharp cutoff nature. Now we are looking for a low pass filter where your signal is almost near to baseband, and the implementation of a low pass filter becomes very easy, right? So that is what I meant here with respect to channel selection. And one more additional thing is we did not look at this aspect actually before. Probably there are when we do an activity, probably in next class or next to next class we'll be looking at certain activity questions based on the receivers, because we were have like all the previous lectures we had theoretical understanding on various type of architecture. So we look at some practical scenarios also. So there we will see this aspect little more detail. I'll write this point here. The mixing spurs. So spur is nothing but unwanted frequency. So since there is no heterodyning process happening here, the number of unwanted frequency components generated are less. So I'll write here as mixing spurs are less. I'll write it as less. So mixing spur is nothing but unwanted frequencies which is generated by mixing of signals itself within the receiver. So and this is possible, or this usually happens when you have heterodyning, when you have different frequencies and that undergoes mixing process, right? Now that is considerably reduced in the case of a direct conversion receiver, right? So these are the benefits, and the main thing is actually the absence of image. Now, okay, so let me, after understanding these advantages, before we may look at the architecture also. Let me just draw the architecture of direct conversion. So architecture will be very simple. So you'll have an antenna. Antenna will be followed by initial band pass filter, which can actually select a band, followed by LNA. So these things will remain same for any architecture because it is working at RF. So you'll have a band pass filter and an LNA, and after this we will actually use a mixer. So here you have RF input, and here you will actually give LO input, and this will be directly pushed to baseband, and we can actually employ a low pass filter here. And that low pass, after this low pass filter, the result here is actually a baseband, right? So the rest of the processing can be done here. Now if we look for a quadrature implementation, same thing, we'll have two arms, upper arm and lower arm. So we'll have an LNA followed by mixer and low pass filter. The same architecture with this is with quadrature down conversion. We have this again a low pass filter with a Q component here, and this arm will be with cos omega LOT, and this will be with sin omega LOT. But we understand that this omega LO is equal to omega RF. So if this is RF frequency, whatever frequency in is omega RF. So omega RF is equal to omega LO to get the signal baseband at these 2 points. So this is the architecture looks very simple because we need to select a band, amplify it, and then mix it and do mixing and get the baseband component. So the architecture looks simple, but when we see the simple architecture, there are some so what to say, there are some issues associated with this direct conversion receiver. So all right, there are some comments here. How will we match RF to LO? Isn't achieving exact match extremely difficult? Yes. All right. Yeah, that is an issue in the sense, but there are methods actually to track and generate the same frequency. Yeah, whatever you have commented as a phase locked loop will actually help in this. So whenever we draw an oscillator is actually, especially in a receiver, oscillator is actually sitting inside a loop where there is some feedback mechanism involved, and we call that as a phase locked loop, right? Because in order to synchronize the signals, the clock signals, we should actually use phase locked loops. Probably, no, definitely we will look at the PLL aspects in the last unit. Yes, but it'll PLL should be there, or the need of PLL is actually there in almost all receivers. Um, the meaning why this DCR, direct conversion receiver, is simple is because of the less number of filters that we were employing before in all the previous architectures to remove images. So that is the great relief when you look in that way, right? But nonetheless, there are issues, and we may look at the issues of direct conversion receiver now. There are a lot of issues. We will be focusing only on one or two issues, and uh, and there are all these issues can be addressed in one way or other way. Um, and many of the issues also appear in heterodyne receivers also, but I'll tell you one by one. I can explain one by one. So let us see the first issue. The very first issue is actually LO leakage. The very first problem associated with the direct conversion receiver is something called as LO leakage. So let us understand what is this LO leakage. LO leakage is nothing but the leakage of local oscillator signal. So to get a picture of that, what I will do is I'll take the receiver part. So from antenna, we have an LNA, and after LNA, so I'm just neglecting the filters in the path because our focus is only this LO leakage, right? So we'll have a mixer, and mixer is fed by a local oscillator, right? Now, so local oscillator is actually a very strong signal which is generated here in order to down convert the incoming signal, right? But now what you can see here is uh, local oscillator is generating a signal locally within the receiver, and if you look at the path, if you look at the signal which is generated at this point, um, the problem of LO leakage is nothing but this direct conversion receiver will emit. This is actually a receiver, but this receiver will emit a fraction of its LO or local oscillator signal from its antenna. So this is called as LO leakage. So how this is possible? This is the point where your LO signal is generated, and from here this LO signal is actually finding a path to travel from this point to the antenna, and thereby antennas will start emit a fraction of it is not the entire LO signal is passing through the antenna, but even though this is an intended receiver, this antenna tend to transmit a portion of LO signal. So how is that possible is because the LO signal is coupled to antenna. LO signal is actually finding a path from this point to antenna, and the path is this actually. The path is through this mixer, and through this LNA. So this is the path. So let us understand how this happens. So say you have a mixer here. Say for example, I am using a passive mixer. So a MOSFET here. Now this is the point where I'm actually feeding the yellow signal, and this is towards the input side and this is towards the output side, right? But we know that there are MOSFET structural capacitance that will actually that exist between the terminals of the MOSFET. Right. Now, when this terminal or this node, this terminal is carrying a particular signal, the signal will be coupled to the other terminal through the structural capacitance of the MOSFET. So that is what we can see here. So when we explain that with respect to a mixer, what we call is the yellow signal will be coupled to the antenna through the device capacitance. So there is a device capacitance between this yellow and RF port. So I'll consider this as yellow and RF port, and there will be some capacitance, some parasitic or structural capacitance exists between these two terminals. And this device capacitance between this yellow and RF port will actually enable or will provide a path for the yellow signal to actually to transmit. That will happen from. So let me draw that here. So this is capacitance. If there is a capacitance here, yellow signal actually can find a path to reach to this point. Now again, you have a low noise amplifier here. Low noise amplifier also will be definitely implemented using MOSFET based structures, right? So say I'm using a common source kind of topology there, where this is input and this is output. There also you can say that you can find that there can be some interaction between these two terminals through the CGD capacitance, right? So that means I can find another path from the input and output of LNA like this. That means whatever signal which has taken the path from LO to RF can definitely get a path from the output to input of this LNA also, right? So let me make that point here. So what I am stating here is the LO signal will get coupled to the antenna basically through the device capacitance. All right, a portion of LO signal, low amplitude LO signal, low frequency LO signal. Frequency is same. The frequency is same. Maybe not the entire signal because no. When I say a fraction is passing here, you can see that there are capacity dividers here, right? There are two capacitors connected here. So whatever is a signal reaching here depends on the amount of capacitance there, right? So the frequency remains almost the same because there is no nothing is no frequency translation can happen here. The only thing is the strength of the signal can be weak. That is why I stated that a fraction of LO power, right? So device capacitance between the local oscillator port and the RF port of mixer, that is one path. And the second is, so the device capacitance exists between the RF and LO port will actually give one path for the LO signal to reach to the input of mixer. And the second path is the device capacitance between input and output of LNA. Right. So these two will completely ensure a path from the local oscillator point to the antenna point. So apart from this, we know that the entire components will be integrated on a single substrate. So in that cases, the signal can also couple through the substrate also, right? The signals, some signals may also couple to the antenna through the substrate. So I can also think about an additional path which directly come from substrate from this path. So let me use a different color from LO to antenna through the substrate. So anyway, we have a strong signal path coming through the capacitive, through the structural capacitance. All right, Siddharth, please hold on. I'll come back. Yeah, your question is valid. Your question is why the situation is not considered in the previous architecture. So when I say previous architecture, the architecture what we considered before is a heterodyne architecture, right? So definitely LO leakage is present even in heterodyne architecture, but probably you can guess what can be the reason or why the LO leakage is not a significant problem in. Okay, let me complete this and let me end up with the issue, like how it is.
Sure, sir.
Yeah, probably you can only figure it out why we did not consider LO leakage. But definitely LO leakage will be there even in other architecture also, but that is not that serious as the issue which is created in a direct conversion receiver, right? Yeah, so let me just complete this. And the other one is the directly from the substrate. So from the substrate to the input pad of the input pad, or directly to the antenna. That is also through the input pad only, right? So one thing is sure that this, I hope you also will agree that this is a receiver and this is not intended to transmit any signal, right? So I can say that this LO emission, so whatever we called it as LO leakage or this LO emission, is undesirable. This is something which we are actually not, this is not a receiver should do. Right. So now why I'm calling this undesirable? Can you just guess the various issues this can bring to the same receiver or to the other receivers? Can I get some responses from your side? Yes, here there is constraint to match the frequency exactly as omega RF. The LO leakage becomes significant, whereas in heterodyne where there was no particular constraint. Nagaraj, yes, I'll come back to the answer for that. Yeah, receiver is acting as transmitter. Uh, okay, I'm not understanding. Siddharth, maybe
No,
you are
sir, that
speaking.
was the response to Nagraj, sir.
Oh,
So
okay, all right, okay, okay, yeah, yes, Abhinav, yes, it is right. Yeah, as the receiver is acting as a transmitter, this can actually desensitize other receivers which intend to receive in the same band, right? Because this is actually transmitting a signal. This can desensitize other receivers which is trying to receive signal in the same band, because this is an unwanted signal coming going and like this is an unwanted signal actually going into other receivers, and that again depends on the strength of the LO or the amplitude of the LO signal also. That is to the other receivers. I can call it as the victim receivers, right? So even to the victim receivers it is a problem. Now what about this emitting receiver? So this is a receiver which is emitting this signal. What can be a problem for this? Information gets corrupted. Yes, Nikhil, that is true. Can you make it a little more clear how I can say that this LO leakage will actually create some other problem? Yes, Abhinav, it is definitely, it will desensitize. Uh, so you meant to say that it will desensitize the same this receiver itself or other receivers? Destructive interference with the desired signal. Very good. Okay. Now when you say destructive interference, yeah, probably we can discuss that issue. Yes. LO doesn't have a data. RF has data. Both are same frequency, so information is lost. Yes. Yes, correct. Yeah. So let me tell that. So this LO emission is definitely an undesirable thing, because why it is undesirable? This can actually desensitize other receivers. I'm calling them as victim receivers. Again, this is a problem even to the emitting receiver also. Right. So let me answer to one question. So why this is not a major problem in a heterodyne receiver is because the LO signal will definitely see. Now you can see that this is RF, this is LO, both are at same frequency. But in the case of a heterodyne receiver, the LO frequency is not same as RF. So if we are choosing LO frequency in such a way that if this is falling outside the band of RF, definitely the LO leakage is not going to affect anything, because we do have filters. So even the LO leakage which is going out may not, if it is outside the band of the intended or the victim receivers, definitely it is not going to desensitize those receivers. Now coming to the emitting receivers, whether it will be a problem to emitting receivers in the heterogeneous receivers, the problem is actually less, because the LO signal is not exactly in the range of RF, it is actually a lower signal. Right. Now, we will discuss the second issue as the result of this LO leakage only. Before that, one way to resolve this LO leakages, so the problem is the LO signal is coming here and going to the antenna, right? Now, if we can employ a differential oscillator, and if we can make the path from this LO to this antenna symmetric, say you have an LO oscillator which is actually differential. So now differential oscillator will actually emit signal. One will be this and other will be actually differential in this way, right? Now, if I am ensuring that there is symmetry in the path from this LO to the input, there is symmetry in the path from LO to the input, both the signal which reaches this antenna will be of the same, will be equal in all respects, and that will be actually get cancelled, right? So this is one possible solution. So let me just write one of the possible solution here. If we give symmetric, okay, let me write it at the next page. Say this is our structure. Now this is LNA, this is mixer, and now if we try for a differential oscillator which will provide signal here in this way and in this way here. Now from this point to this point and from here to this point, if we ensure that the symmetry, so if we have symmetric layout for symmetric layout of oscillator and the RF signal path, we can, in effect, we can actually cancel this signal, right? So one way to resolve this LO leakage is basically by ensuring actually the cancellation of the signal. All right. Under the question is what is meant by symmetricity? Okay, is symmetry. So now from the LO signal, symmetry in the sense symmetry of the layout itself. So you have a lot of components here, right? Now, if your LO signal, if from the oscillator, if there are two paths, one from this side and one from the other side, now the elements or the way we have performed layout for this particular circuit should be in such a way that both signal or both paths should affect the LO signal equally, right? Both signals should affect both paths should affect the signal equally, so that the signal appearing at these 2 points also will be equal and opposite. Now if there is no symmetry layout, what can happen is, even though you have a differential oscillator signal at these 2 points, when it travels through the paths available from this LO to the antenna, there can be variation. Definitely there will be variations to the signal, and if that is coming as different, then the complete cancellation of this LO may not be possible, right? So a symmetry layout or a symmetry in the chip layout will actually help in this. So we haven't looked at such kind of things, and this, I think this is something we need to discuss. Even for current mirrors, you would have studied about current mirrors. So whenever we do a chip implementation of any circuit, the accuracy of the circuit, especially in the case of current mirrors or in the case of in RFIC in those oscillators, we have to actually look at the layout in a very detailed way, right? Because the accuracy in current mirror is also depending on how we are performing the layout of the current mirror structure. In a similar way, here also, in order to cancel the signal completely, we should actually look at the symmetry in the layout. I hope I answered you, Anirudh. I'll come back if you have questions. Varying the phase of the yellow signal. Okay, I didn't get that, Sagar. By varying the phase of the yellow signal, in the sense, how can we do that? If it is a single signal coming in, that is what by differential LO, that is what we are actually doing, right? Because when you say the signal is differential, which is equal and opposite, that is what we actually did by having a structure something of this form. We have to ensure that the oscillator is differential. Situation where constructive interference may occur here. Nikhil, I didn't get that.
Sir, we have two paths, right? Here.
Yes, yes.
Sir, what if a situation occurs such that they both constructively add instead of cancelling out each other?
Then that will lead to a larger signal, right?
So this solution would not be so promising
No,
then.
yeah, that won't be a solution actually. Now, when you have two signals, which is as you are telling, if it is constructive interference, if it is happening, definitely that will result in a larger LO signal, which can create so serious problems, right?
Yes, sir.
Yeah, Siddharth. If it is differential, there is no scope of constructive interference. All right. Okay. So. Okay. Thank you for the interaction what you are having now. Let me just complete this. Okay. So now we will see what is a problem to the emitting receiver now. So we know that LO leakage is happening and that can be avoided, or we can cancel those leakage by employing a symmetry in the structure. But now what is the actual problem for the emitting receiver is we will discuss it as two. This LO leakage will result in some large DC offsets. I hope you will understand this. We have LNA that will result into a mixer, that will lead to a mixer, and here is your LO signal, and this is the signal. Right now, say omega RF signal. Say we have a signal which is VRF cos omega RF T. That is an incoming signal, and we have a signal here which is VLO cos omega LO T. Right now, if a portion of this LO is reaching at this point, it is emitting. At the same time, it is available at the input of this receiver also. That means if this portion is coming in, or now what the LNA is receiving here is you have VRF, which is the RF signal. Along with that, you have a portion. Let me write that portion as some k times VLO. Right. So because of this path, even a portion of LO signal is actually available at the input of the LNA. Now, whatever is coming into the receiver is the RF signal. Along with that, a portion of LO signal is also coming in. Now, can you tell me what will be the problem here? Now, what will happen inside this mixer? What will happen inside this mixer? IF won't be 0. Why IF won't be 0? Because all are same frequencies, right? Yes, yes. Clipping. All right. Yes, Sanidu. There will be a DC component coming in. If you remember what we have discussed in our first class is we have written the various components as a part of non-linearity, right? Now you know that there is an omega LO component here. You have the same omega LO component here coming in. Now, when you have when mixing of two components of same frequency, that will definitely result in a DC component. That is okay, Nikhil. Yeah. So that will result in a DC component. So DC offset will be the problem here. So you will have definitely a VIF. So when even if I write VIF, that is actually your it is not an intermediate frequency. That is actually the baseband, or the it is baseband frequency, but before filtering. But along with this, we will definitely have a DC component here. Right. I hope this is clear. So what is happening here is, along with the desired signal, so VRF cos omega RFT is the desired signal. Along with that, we have a leakage component which is K into VLO. right? That is also appearing at the input. Now along with the desired signal, this component will also get amplified and also will get mixed. So here it will be amplified, here it will get mixed. Now this VRF plus KVLO is actually mixing with the VLO component itself. So this is this we call it as self mixing, because a portion of LO component is getting mixed with LO component itself. So this is called as self mixing or LO self mixing. So whenever the self mixing happens, that will result in a DC component, and that DC component will be definitely in the baseband, right? DC component in the baseband, because we are multiplying a sinusoid with the sinusoid itself, that result in a DC term, right? So this DC offset is actually a problem, because can you tell me why this DC offset can create, or how this DC offset can create a problem? Any answers? Compression. Yeah, desired signal is at baseband. Yes. Mm, Extraction of information becomes difficult. Cause clipping. Okay, clipping occurs at. Okay, so you meant to say that. I didn't get that. How you are telling clipping will occurs? Compression. Okay, to signal. Signal level is raised. Yes, operating point variation, higher power loss, power dissipation. Yes. So what happens is, now the signal, or the a signal which is down converted, should be processed by a circuit. We generally call it as baseband circuit. There will be some set of baseband circuitry here, right? Now there also you have components. There also your components should actually operate in a specific operating point. Now if this DC component is a large DC component, if this is resulting in a large DC component, those DC components may affect this baseband circuit, and even this baseband circuit can actually get saturated in the sense, say for example, you have a signal, you have a circuit which need to be operated, and you have set the operating point, but a large DC is coming in, and that incoming large DC can actually vary the operating point as a whole, right? So that depends on the amplitude of the signal coming in. That is that that depends on the DC value. Let us look at one example to understand this in a better way. Just a minute. So the point here is, the large DC offsets can affect the baseband circuitry. Baseband circuitry operation, right? Okay, so let us conclude the class with dealing with this specific problem. Let us look at this example. You have a direct conversion receiver. There is a direct conversion receiver which incorporates voltage gain of 30 dB from LNA input to each. Yes, Saurabh, what determines the magnitude of the DC? Yeah, let us see that here. That depends on the magnitude of DC offset depends on the gain of previous stages. We have LNA gain, we have mixer gain. So those things also will affect the magnitude of DC component. So voltage gain of 30 dB from LNA input to each mixer output. And another gain of 40 dB in the baseband stages following the mixer. Now the question is, if the LO leakage at the LNA input, if the LO leakage at the LNA input is minus 60 dBm, determine the offset voltage at the output of mixer and at the output of baseband chain. Right. So the question is this. Yeah. The question is this: there is a direct conversion receiver which is incorporating a voltage gain of 30 dB from LNA input to mixer output, and another gain of 40 dB in the baseband stages following the mixer. Okay. Now the LO leakage at the input of LNA is minus 60 dBm. What will be the offset voltage at the output of mixer and at the output of the baseband chain? So you can think about the same architecture and you can try to work it out. Nagesh, your question is, will the DC offset due to the LO be constant at all the time? Due to the LO. So that if the LO leakage component, see, I have written here the LO leakage component is minus 60 dBm, right? Now the LO leakage component, if this remains 60, if this is always 60, and if the gain provided by the other parts are also same, then the leakage component also will be same. The DC offset generated will be same always, right? But since it is a leakage component, we cannot say that okay, every time the leakage will be only 60. We cannot say that, right? So I think we have very less time to finish this. Okay, you guys can try this question. We will start the discussion. We will continue this in the next class, and we'll wind up this unit. And we'll start a third unit probably from the next class, right? So today what we have discussed is, we discussed about direct conversion receiver. We started with we started with the understanding of a direct conversion receiver, where we are looking for a zero IF, right? So where your omega LO is equal to omega RF, and the benefits of direct conversion receiver, the main benefit is the absence of image, and that result in that simplifies the design a lot, right? Then we looked at the architecture and the issues with there are a lot of issues and there are solutions also, but the one main issue what we discussed is LO leakage through the parasitic paths available from the LO to the antenna, and this will affect both the emitting receiver and the victim receiver. Now for the emitting receiver, this will affect as a large DC offset which is appearing at the baseband, which may affect the operation of the baseband circuitry. And for the victim receivers, those receivers will also receive an unwanted signal in their band of interest, right? Now probably now this is clear. Now it is clear why this issue is not why this has not come as a major issue in a heterodyne receiver, is because in a heterodyne receiver, even though this LO leakage is present, this LO leakage or the LO signal is actually LO signal is taken outside the band of interest, right? So that will not affect the victim receivers, right? Now even for the emitting receiver, if we consider as emitting receivers, yes, the LO leakage is a problem, but the problem is not that great as in the case of a direct conversion receiver, because we are directly getting a signal at baseband. Our signal is also down converted into baseband, but in the case of heterodyne receiver, that is not the case, right? We do have intermediate frequencies, and we are actually processing at some intermediate frequency, not directly in the baseband. So that is all about the architecture of direct conversion receiver and the issues associated with this. So try to work it out on this problem, and we will discuss this in the next class. So thank you so much for listening.